In this video, we're going to do another example of optimization. So here we have a 4-foot piece of wire and we are going to cut it and shape one side into a square and one side into a circle. We also might not cut it and then just make one of the shapes. And we want to know what's the maximum area that the figures can enclose. So either a single figure or the joint of two figures. So to see a little picture of this, so let's imagine that this is our wire. Okay, so it is 4 feet long. Okay, and then we're going to cut it at some point. So let's say we cut here. And we're going to make one side, let's say this one, into a square. Okay, and then the other side into a circle. So we need some variables. There's different ways that you could label this this problem. I think it's easiest if we label it from the shapes we're going to make. Okay, so let's say that this is x by x, because it's a square, the side lengths are the same. And let's say that this circle has radius r. Okay, because then we know we want to maximize the area, which is going to be a, which is going to be x squared plus pi r squared. Okay, so then this equation is easy to construct. Okay, now obviously there's too many variables here. There's x's and r's in our a equation. So we want to get rid of one of them. So what we're going to do is we need to use the fact that we only have 4 feet of wire. Okay, now this is a little bit potentially confusing to make the constraint equation. So let's think about it. How much wire, we use this amount of wire for the square. Okay, so that means that that part went all the way around like this. Okay, similarly on this side, we use this amount of wire and that went all the way around the circle. Okay, so the amount of wire, so the 4 feet, constraint. So our constraint is that we have 4 feet of wire, and that has to equal the perimeter of the square. Actually, instead of writing it, I'm just going to do a shape here. So the perimeter of the square plus the circumference of the circle. Right? Because that's the wire that we actually used. So what that means is that 4 should equal, so the perimeter of the square is easy, so we go x, 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 so it's going to be 4 x's. Okay, now the circumference of the circle, you need to remember the formula, so the circumference is 2 pi r, okay, for a circle. So this is our constraint. So we want to use it to get rid of one of the variables above. It doesn't really matter here which one we solve for. I'm going to solve for x, say. So 4x is going to be equal to 4 minus 2 pi r, which means that x is equal to 4 minus 2 pi r over 4, which we could simplify to 2 minus pi r over 2. Okay, so that's our x. Okay, so here we solve for one variable. Okay, it doesn't matter which. And then what we're going to do is we're going to plug it in up here. Okay, so that our area is going to be only in terms of r. Okay, now maybe I'll just write here. So this one is my constraint. Okay, so that means that the area is actually 2 minus pi r over 2 all squared plus pi r squared. Okay, so now I have the area in terms of only r. Now we can take the derivative. So you could simplify this if you want to, and then take the derivative. I'm going to simplify it a little bit, but I'm going to not expand the square. I'm just going to use the chain rule to take the derivative. If you want to expand the square, that's perfectly fine. So I'm going to write this, so you could think of this fraction as 2 over 2 minus pi over 2 times r. Okay, so that's going to be a little bit easier for me to work with. Okay, and that's squared plus pi r squared. So then a prime, so we take the derivative of the first part, so we bring the 2 down, and then it's 1 minus pi over 2r to the power 1, and then I have to multiply by the derivative of the inside, so the derivative of 1 is 0, and the derivative of this part is the constant, so it's a constant times r. So this is negative times negative pi over 2. And then the derivative of the pi r squared is just 2 pi r. Okay, so that's my derivative. Maybe let's simplify it a little bit. So I need to put the 2 through, and in fact the negative pi over 2 through. Okay, so what I get is 2 times negative pi over 2, so that's just negative pi. And then I have 2 times negative pi over 2r, so that's negative pi r, and then times another negative pi over 2r, I'm going to get plus pi squared over 2 times r, and then plus 2 pi r. Okay, so that's my derivative. So now I want to find my critical numbers. So I want to think, where is this derivative equal to 0? So that's negative pi plus pi squared over 2 times r plus 2 pi r should equal 0. So I'm going to move this pi to the other side, so I'm going to add pi, and then I can factor out the r on this side. Okay, that's going to equal pi. So then I can divide by this. So r is going to be pi over pi squared over 2 plus 2 pi. And I see that I can factor out a pi, which means that I can cancel 1 pi everywhere. So I'm going to have 1 over pi over 2 plus 2. I don't really like the way that looks, so I'm going to multiply by 2 over 2, just so I don't have a fraction on the bottom. So this is going to be 2 over pi plus 4. Okay, so that's my r value. And in case you're interested, it's approximately 0.28. So what we want to think is that in our domain? So does that r make sense? Well, yeah, I could have a circle. I mean, the r definitely needs to be bigger than 0. And it's small enough that we probably didn't use too much wire. So that's my, and then, oh, I should also check where the derivative does not exist. Okay, I don't need very much room for that because it never happens, right? It's a linear in r, so it exists for all r. Okay, so now we want to think, we have only one critical number. Okay, so this is our critical number. So using the critical point theorem, we want to maximize the area. So we're hoping that this critical number gives us a maximum. Okay, so we will need to verify that it actually is a maximum. Okay, so I want to see where is it a max or min. So there's different ways to do this. You could use the first derivative test where you look for increasing, decreasing. I'm going to use the second derivative test. Okay, so it doesn't matter though. Maybe I'll just write here. Because the derivative of my critical number is 0, I'm allowed to try to use the second derivative test. So I'm going to take the second derivative. So if I look from this sort of simplified one, Okay, there's my derivative. The derivative of negative pi is 0. The derivative of this term is just the constant in front of r, as is it here as well. So my second derivative is going to be pi squared over 2 plus 2 pi. Okay, notice that there's no r's here. So what that means is when I want to plug in my critical number, 2 over, oops, is it pi? Yeah, pi plus 4. It's just equal to the number, pi squared over 2 plus 2 pi. Okay, so that means this number is positive. Okay, it's a positive number. So that means that my graph is concave up there. So if it's concave up and we have a critical number, it actually needs to be a minimum. So r equals 2 over pi plus 4 gives a minimum a value. Okay, that's not what we want. Okay, so that's a problem. So we're getting a minimum. So where does that mean? Do we not have an extrema, an absolute max? Well, it turns out that we do here because we actually have a closed interval domain. Okay, so here our domain is actually a closed interval. Okay, so I don't know off the top of my head what the biggest r can be. Okay, but I know that r is at least 0 and it could be 0. Okay, as is x. Okay, so that means that the endpoints arise when r equals 0 and when x equals 0. Okay, so these are when we only make one shape. Okay, so when r is 0, this is when we make only a square. Because there's no radius, so we didn't actually make a circle. When x is 0, we didn't make a square, so we made only a circle. Okay, so those are our endpoints. So now I'm just going to check each of them. Okay, so if we do if r is 0, that means we made only a square. Okay, so okay, we should have 4, the length of the wire is equal to 4x. Okay, this is our constraint. Because we didn't make a circle, the perimeter of the square had to be our full wire. Okay, so that means that x equals 1. So our area is going to be just x squared, which is going to be 1 squared. So 1. I'll pick a different color here. Okay, if x is 0, then we made only a circle. So our constraint is 4 is equal to the circumference of that circle, 2 pi r, which means that r is actually 4 over 2 pi, or 2 over pi. Okay, does that make sense? Hopefully. So the area here is pi r squared, because we only have a circle. Okay, and r is 2 over pi. So this is going to be pi times 4 over pi squared, which 1 pi's will cancel. So this is actually 4 over pi. And 4 is bigger than pi, so this number is bigger than 1. Okay, so that means it's bigger than this area. And in fact, it's bigger than the area when we had our critical number. But you could check you could check that if you wanted, but we know that that one gives a minimum. Okay, so that means, it is best not to cut the wire and to only form a circle. Okay, now what was the question asking? To make sure we answer it, what is the maximum area? So we actually want the maximum area. Okay, so this will give maximum area of A equals 4 over pi, which is approximately 1.273. And that should be, the units are feet, so feet squared. Okay, so this would be our final answer here. Okay, so here's an example where the critical number, we only found one critical number, like often happens actually, but it was the wrong one. This is why it's so important to check that you found the right critical number, okay, because it can be a wrong one. It's not usually, okay, but it can be, and if it is, then you need to think about what happens at the endpoints. Okay, here we actually had a closed endpoints. They actually meant that we only made one shape, so we just computed the area in each of those instances.